Molecular forces in phase diagrams, lecture number 10. So we've talked a lot about making the bonds that occur within molecules or compounds, that the attraction between one atom to another. Now we're going to sort of step back and look beyond a single molecule and look at the interactions between one molecule and another molecule. So what interactions do we have between those two things, right? And that's what we're referring to as these intermolecular forces. Right? So we have these two different types of forces that were at play here. We have the intramolecular, those bonding forces, the positive minus in the ionic bonding, or that sharing of electrons in the covalent bonding. Those are within play inside the molecule, or intramolecular. Right? And that's what holds the individual atoms together, right, within the molecule. And those intramolecular forces are going to be true in no matter what state that molecule is in or where it's at. But we're also interested in these so-called intermolecular or non-bonding forces, the forces between those molecules. Right? And those forces are what are going to be different depending on the state that those molecules are in. And as we separate those molecules, as we move from one phase to another, it's those intermolecular forces that we're trying to overcome. Or as we go from between a gas state to a liquid, those are the forces that are causing that interaction. So we're going to spend quite a bit of time now talking about those intermolecular forces. If we look at this is what we call a phase diagram. This is the phase diagram of CO2. So it relates the excuse me, the pressure the compound is under versus the temperature. So it's this relationship. And as you can see, as we either vary the pressure or vary the temperature, where you can move from one state to another. The solid, where we have sort of limited mobility, high attraction between molecules, very stationary, to the liquid, where we get more energy, less attraction between molecules, more movement, to the gas phase, where we have very little interaction between the molecules, essentially none, because they're far away from each other, more energy, higher speeds, those types of things. So this relates that. So what we're typically think about is a single pressure and what changes can occur as we go across at that single pressure. But the lines on this phase diagram represent those changes between, say, a solid and a liquid. This first one, where we get melting or freezing. All those places along that line, those two phases are in equilibrium. So the molecules have the same ability to move back and forth from the solid to the liquid back to the solid. There's sort of an equilibrium line there. But we can also have, as you see for CO2, under atmospheric pressure, right down here, we can have that ability for the CO2 to move from the solid straight to the gas through this process called sublimation. Right? That's what that line occurs here. So when we talk about sublimation, we're moving from the solid to the gas. Right? Same thing with when we go from the liquid to the gas, or the gas to the liquid. We have that other line back here, which corresponds to the vaporization or condensation. All of these processes are going to be equilibrium process. When we're on the line, both proper states are possible. Right? A couple of different points or places on this diagram I want to point out, particularly this triple point down here at the bottom. That's where the line for the melting, freezing, and the vapor pressure and sublimation all come together. All three of those lines connect at that point, the triple point. So all three, the solid, the liquid, and the gas, are in equilibrium at that point. Right? So we can have a gas molecule can move from a gas to a liquid to a solid, have the same probability, sort of. The other one is up here on the corner, this so-called critical point. It's where the density of the gas and the liquid are equal. Right? So we can no longer really distinguish between a liquid and a gas. Right? That equilibrium process runs out. Past that, where you can see it's sort of fuzzy, that is what we call a supercritical fluid and there's some people that are suggesting that that should be a fourth state of matter, but we're not going to get into that. It's usually under high pressure, high temperature. We can it has properties of like a liquid. The molecules are being forced close together, but it has also those interactions like a gas, that they're moving at such speeds that there's very little interaction. So it has very different properties. One should be aware of those 2 points. But all three of these phases are dictated by the interaction of the one molecule to another, these so-called intermolecular forces. Right? And here we have a list of those intermolecular forces, and they depend on the types of molecules that we have, and whether we have a pure compound or pure substance where we only have that type of molecule, or we have a mixture or a solution where we have two different kinds of molecules. The interactions are going to be different depending on what we're looking at. Typically, we think about in these intermolecular forces that one molecule interacting with another molecule of the same type. Right? Those are sort of the easiest to see. But if we have this mixture, we also have to take into account those. So all possible intermolecular forces are listed here. Right? The first one is what we call the ion dipole. So this one, since we have two things, we must have a mixture. Right? We have to have one species that is ionic, right, has a charge, either positive or negative, and then something else that is polar. Right? So there's a separation, a partial charge. And those interact, it's not going to be as strong as an interaction as the positive to the minus in an ionic bond, because that in the dipole, that is not a complete charge. Remember, it's a partial charge. But there is still this Coulombic interaction where the plus or the minus is interacting or attracted to the partial plus or minus from the other one. So we can think about these ionic, like salt in water, the sodium interacting with the water molecule. That would be an example of this ion dipole interaction. These are also listed in strength, so we're going to jump down and talk about another one which is sort of simpler to see, with this is dipole-dipole interaction. So this can either be in a mixture or a single molecule interacting with another molecule of the same type. But this is what occurs when we have something that is polar. Right? We learned recently about looking at the three-dimensional shapes and how those differences in electronegativity are summed across those shapes to get us a polar molecule. So if we have a polar molecule, that is capable of having this dipole-dipole interaction. Right? So we have this polarity, the partial positive side of one molecule is interacting with the partially negative side of the other. A special type of these dipole-dipole interactions is what we call the hydrogen bond, the one immediately above that. It's higher in strength, and it comes about because of the exceptionally high electronegativity of nitrogen, oxygen, and fluorine. So we're looking at a hydrogen that is directly bound to one of those three atoms, a nitrogen, an oxygen, or a fluorine. And we can get a special interaction then, because we're pulling those electrons so hard that we get a very large dipole in those situations. So we can recognize those simply because we have a hydrogen directly bound to an oxygen, nitrogen, or fluorine. Right? Otherwise, it's just a dipole-dipole interaction. The behavior is the same, it's just much stronger. And this is what this water is the prime example of this, again, because it's got that hydrogen bound to the oxygen, gives us some special properties. It's what this hydrogen bond is what makes water less dense, or ice less dense than water, so ice floats. It also gives if you follow the density of water, the density is highest at 4 degrees Celsius, for example, instead of at 0. So it's this special hydrogen bond that's allowing those properties. Right. If we move down the list to slightly weaker force, we see that we have this ion now with something that's traditionally not polar, this induced dipole. So what we're doing is the presence of this present charge, the plus or the minus, as it comes in contact or close proximity to another atom that's not polar, right? If this is positive, as it comes close to this one, the electrons that are in this nonpolar molecule are going to be attracted to this positive charge. So they're going to sort of migrate towards that and induce temporarily a dipole moment because the electrons are moving within the molecule. Right? So the ion is inducing a dipole in another one. So we can take something like the example here, iron 2 plus in oxygen gas. We bring oxygen or oxygen liquid. We bring it close to it in this iron, it's going to have a strong interaction because the charge, this 2 plus, is inducing a dipole in the oxygen. This ability to form or have a dipole induced is through a property we call polarizability. It's a function of how easily the electron cloud of that atom is distortable. Right? So we can think the bigger the molecule gets, the easier it is to distort that cloud. So we typically see as molecular mass increases, the polarizability of that molecule is going to increase. Right? And that's going to have a direct effect later. Right? The next one down, this dipole, induced dipole, same process. We have this partial charge inducing a smaller charge in another typically non-polar molecule because of the presence of this polarizability. The last one is the dispersion or London dispersion or van der Waals forces, which is really an induced dipole interaction. That as molecules come close together, there's an ability that the electrons are going to move away from each other, or since their electrons are sort of constantly moving, there's a potential that at any given time that molecule is going to have a temporary dipole. Right, which means it's going to be attracted to another molecule that also has a temporary opposite dipole. Right? So all molecules are going to be capable of showing this dispersion or London dispersion interaction, just because of the movement of electrons. That is sort of our base intermolecular force. All molecules have this dispersion force. The rest of them depends on the molecule. Right? Some of them you have to have two different types of molecules present. If all of these induced intermolecular forces require a mixture of things. Again, this shows the strength. The highest interactions on top, the weakest interactions here on the bottom, as we would expect from the sort of severity of the charge. The ion dipole interaction, we have a positive or negative charge and a partial positive or negative charge interacting. We would expect that to be fairly strong. Down here at the bottom in this London dispersion forces, we have sort of this temporary situation where they're attracted to each other. Should be fairly weak. So let's look at what happens as we go across this phase diagram. So remember, the phase diagram shows the pressure versus the temperature. If we select a pressure and either increase or decrease the temperature, let's follow that process through a molecule. So let's look at what we call the cooling curve for water. So say we're in the gas state for water, and we begin at a constant pressure to begin cooling that gas down. Right? As we decrease the pressure, remember from our conversations last semester about gas laws, as we decrease the temperature, our energy or this average molecular speed is going to decrease, right? Which is going to cause those gas molecules to become closer in contact to each other for longer. As they get allowed to come closer, these intermolecular forces are going to begin to take effect, right? Until we get to the boiling point, right? Where that temperature where there's enough energy to cause the liquid to turn to a gas, or the condensation point where there's enough that the gas is going to become a liquid. Right? At which point now we have the ability that gas molecule can either be condensed into a liquid or come out into stay as the gas. Right? That's sort of an equilibrium process. So it takes more energy to be lost before the primary possibility for that molecule is to be in the liquid. So there's this amount of energy that has to be lost due to those molecules just slowing down. Right? At which point we get into the liquid state, And then we can see we can decrease that temperature. Now the intermolecular forces are strong, the molecules are fairly stationary, so there's a good chance that those intermolecular forces are going to be holding on to those, right? Until we get to the freezing point where now those molecules have lost enough kinetic energy that they're essentially stationary and being held together by those intermolecular forces. So there's not enough kinetic energy within the molecules to overcome those intermolecular interactions. And that's the way it's going to be when into this solid. Right? They're going to sort of arrange themselves into their crystals and sort of be stationary and vibrate, not being able to overcome these intermolecular forces. So the way we can calculate these energy changes is the same way we calculated energy changes last semester, using this Q equation. Right? So we're talking about the heat in present. For the things where they are in a specific phase, so whether it's a gas, a liquid, or a solid, then the heat associated with that is equal to the number of moles of the gas times the heat capacity of that species under those conditions. So that number, this C, is going to change whether water is a liquid, a solid, or a gas. That the value is going to be different times the change in temperature that molecule is experiencing. At the phase transitions, because we have sort of an equilibrium process involved, and we're essentially the two can move back and forth, it has to lose or gain some energy depending on which way you're going for it to finally make that transition complete. There, our Q is dictated by the number of moles present times the delta H of this process. If it's at the boiling point, then that's the delta H of vaporization. If it's at the melting point, that's the delta H of fusion. Right? But having these values, we can follow this Q value change through these various steps. So the second one's used for stages 2 and 4 on this diagram. So we can talk generally about these two conditions where the gas, we have very little intermolecular interactions, so the intermolecular forces aren't at play very much because those molecules have high energy, not very close together. In the solid state, those molecules are completely dominated by those intermolecular interactions. They're frozen in place. There's not enough energy to overcome those intermolecular interactions, and they're sort of stuck. Right? During the liquid phase, we have this other where there could be enough energy because those molecules are moving that we're forming these intermolecular interactions, and then they're breaking them, right? Which is going to allow us to not only talk about the molecules moving within the liquid, but also it gives us the potential for those molecules to break out of the liquid state and become a vapor. Right? And this is what we refer to as the vapor pressure. Right? As the vapor pressure is going to increase as the temperature increases. Right? Vapor pressure is a measure of how many molecules, if you will, are able to break these intermolecular interactions and become a free molecule separated from everything else, a gas essentially. Right? So as the temperature increases, the kinetic energy is going to increase, the likelihood that it's going to be able to break those intermolecular interactions is going to increase. So we should get more molecules in the gas phase. Remember, from our gas laws, the more molecules we have, the higher the pressure we have. Right? And conversely, the strength of those molecular interactions is also going to play a fact. Right? So the stronger the intermolecular interaction, the harder it is for that molecule to break free, which means a stronger intermolecular interaction at the same temperature is going to have a lower vapor pressure. So the vapor pressures are typically decreases as these intermolecular forces increase. We can calculate these pressures, this vapor pressure, using the Clausius-Clapeyron equation shown here, right? Where we're taking the natural log of the pressure is equal to negative H, or delta H of vaporization, divided by this constant R times 1 over T plus some constant C. Right? So we can then take 2 points, we can look at the vapor pressure of a molecule at 2 different temperatures. Is probably the more useful one below here, where this R value is the 8.314 joules per Kelvin mole. Right? So we can do those calculations fairly simply. We know the pressures and the temperatures are one pressure and one temperature. We can calculate the second. But this vapor pressure is really has a direct result on the boiling point. Once the vapor pressure gets high enough, we're essentially boiling the liquid, right? So the boiling point is the temperature at which the vapor pressure equals the external pressure, right? So the pressure pushing the molecule back into the solution is equal to the pressure of the coming out, right? So that's going to allow that we're at equilibrium now. That molecule is free to choose either state. So the normal boiling point is what we refer to at 1 atmosphere, or the 760 torr, what temperature that occurs at. Right? But if we increase the external pressure, we push the pressure on that liquid increases. The more we push down, the harder it is for those molecules to escape. The boiling point is going to increase. This is the theory behind the pressure cooker situation. So if you've used a pressure cooker, you seal that in, turn up the heat, right? You're allowed to get the contents of the pressure cooker at a higher temperature than normal boiling point, which is going to allow you to cook food faster if you're into that sort of thing.
Dad, I done did it.